Concerning the convergence of power series, we've seen two cases so far. First one was the series converged only at its center. And the last one that we just looked at, it converged over some sort of interval that surrounded its center point. This one turned out to be an open interval. It's not always the case. Anyway, the last one here presents our final case. Let's take a look. Example 3, for what values of x is the series? What a strange looking series. Summation from n equals 0 to infinity of -1 to the nth power times x to the 2n plus 1th power divided by 2n plus 1 factorial. So hey, this 2n plus 1, 2n plus 1, do you remember what kind of numbers those are? Well, here, let's just start plugging numbers in. Let's see what this thing looks like. If I were to plug in a 0 here, -1 to 0, that just goes to 1. 2 times 0, that's 0 plus 1, that's just to the first power, and this is also the same number, so it's like x to the first power over 1 factorial. 1 factorial is just 1, so you can rewrite that, like just x. If I were to stick in a 1 here, -1 to the first, we keep that this time. 2 times 1, that's 2, plus 1 is 3, and then this will be a 3 factorial, minus x cubed over 3 factorial. And let's stick in a 2, right? So 2, that's going to be squared. It's positive. 4 plus 1, that's a 5. And so plus x to the 5th over 5 factorial, minus, and then so on. So we can see that these things, 1, 3, 5, those are odd numbers, right? Okay, okay, this is strange. Whatever, let's just apply the ratio test so we can find out where this thing converges. So we're going to go with the limit as n goes to infinity. And since this is already a fraction here, a ratio, we are going to use the nifty trick where we'll multiply by the reciprocal. Absolute value, we start off with the n plus 1th term, so -1 to the n plus 1, x to the, now n is right here in the middle, so you got to be careful here, put the n plus 1 in parentheses, so 2 times n plus 1 over, same thing on the bottom, 2n plus 1 in parentheses plus 1 more factorial. And now multiply it by the reciprocal of the nth term, 2n plus 1 factorial, beep beep, over -1 to the nth, x to the 2n plus 1. And now here is the most satisfying part, of course, and that's doing some cancellation. But before we can cancel, we've got to simplify all this. I'll have to do some distributive property here. So 2n plus 2 plus 1 more actually makes that 2n plus 3, which is what this would be as well. 2n, here, cancel that out, 2n plus 3 factorial. Now we're ready to do some cancellation. 2n plus 3 factorial is bigger than this 2n plus 1 factorial, so we're going to scale this guy down so we can cancel out some factorials. What's that going to look like? Well, 2n plus 3 factorial is 2n plus 3, subtract 1 from that, 2n plus 2, subtract 1 from that, 2n plus 1 factorial, and now they match up, and I can cancel. Nice. So we're left with these two terms still down here at the bottom. All right, let's tackle the -1 here. This -1 to the 2n, or to the n plus 1, -1 to the n. You just divide out your -1s and subtract the exponents. So n plus 1 minus n just gives us to the first power there. So you essentially just have a -1 up top. Okay, all right, fine. And then finally, let's take the powers of x. It's x to the 2n plus 3. We're dividing that x to the 2n plus 1. You subtract your exponents there. So 2n plus 3, 2n plus 1. The two n's are, of course, going to cancel out. It's just essentially 3 minus 1x squared. So we're left with x squared. This is a complete mess. Let's clean this thing up. Let's make this look a little bit prettier here. So limit n goes to infinity, or absolute value. We're left with a -1 to the first power, so this is -1. We're left with just an x squared up top over, and the only thing, oh, I forgot to actually do the canceling here, right? This was x squared, yeah, okay, yeah. Now it's an even bigger mess. We're left with a 2n plus 3 times a 2n plus 2. Meow. Okay, now absolute value is going to get rid of the negative 1 here. It's going to make a positive 1. It doesn't affect the x squared because it doesn't even matter what I stick in here. This thing is going to be a positive or, possibly 0, whatever. So again, the absolute value doesn't affect it. N is some sort of positive number. It starts at 0. Well, it's 0 and then it becomes positive. Anyway, it makes all of these numbers down here positive. So absolute value, redundant. Let's get rid of it. So the limit as n goes to infinity, negative 1, get rid of it, x squared over 2n plus 3 times a 2n plus 2. Okay, so remember that the variable for the limit is n. It doesn't affect the x squared that's up here. It's only the bottom. X squared stays the same, and these n's just keep getting bigger and bigger and bigger. It's going off to infinity. I take something that stays the same, divided by infinity. This goes to 0. Well, what does that mean? It means that no matter what we stick in here for x, remember, if I just define this as a function here, I get to stick in, I don't know, a positive 1, negative 1, a half, 14, a billion, whatever. Whatever I stick in here for x, hey, where'd my laser pointer go? I'm dividing by a number that's way, way larger than that because it's going to infinity. This is going to be equal to 0. All that to say that since 0 is less than 1, by the ratio test, this converges absolutely for all values of x. It converges everywhere. It converges from negative infinity is less than x, which is less than positive infinity. And that, that one is our best case, right? Remember, we had 3 cases. It converged at its center point. We converged over some sort of interval, and here we converge everywhere. Let's just kind of recap that just for a second here. Here was the ratio test. We went through all the cancellation stuff. We got 0 for all values of x, which is less than 1, meaning that this converges for all real numbers. All right, the only thing left to do, we've talked about how to find the interval of convergence. Next video, we'll talk about the radius of convergence. It's way easier even than all the stuff that we've just done.